Have you ever stopped and wondered how scientists can possibly know what our planet's climate is going to be like, say, decades from now? Well, today, we're pulling back the curtain on one of the most powerful and maybe misunderstood tools in all of modern science, the climate model. And no, it's not magic. It's more like a virtual Earth in a box. So let's dive in. Right, so how can anyone possibly know what our world will be like in 10, 50, or even 100 years? I mean, it's not like there's a crystal ball. It's about building a virtual one. But first, you really have to appreciate the just sheer scale of the challenge we're talking about here. I mean, just look at this. This is what scientists are up against. You've got the sun's energy. You've got clouds, volcanoes, the oceans, ice, the land, what we do as humans. And everything is affecting everything else. The atmosphere talks to the ocean talks to the ice, the land talks to the air. How do you even begin to make sense of all that? Well, you don't guess. You build a copy. You literally construct a virtual planet, a digital Earth, and you run it inside some of the most powerful supercomputers ever made. That's the whole idea behind climate modeling. You can think of it as Earth's digital twin. It's a fully functioning virtual version of our world that lets scientists run experiments they could never, ever run in real life. It's kind of like a time machine that can run forward and backward, helping us understand not just our past, but our possible futures. So what is a climate model, really? At its heart, it's just a massive computer program. But instead of code for an app on your phone, this program is written in the language of mathematics and physics. It uses these really fundamental equations to simulate how all the energy and materials move through Earth systems. Okay, so how do you actually build a planet inside a computer? It's obviously a huge task, but we can break it down into 3 basic steps. So the whole process really boils down to 3 main things. First, you need a map, a kind of digital scaffolding of the entire planet. Second, you need a rulebook. That's the fundamental laws of physics that say how everything interacts. And finally, you need an engine, a supercomputer that's powerful enough to run this incredibly complex simulation. So step 1 is creating that grid. Scientists basically cover the entire globe, the atmosphere, the oceans, the land, with this massive 3-dimensional grid. Each one of these little boxes is a spot where the model calculates things like temperature, humidity, and wind speed. A lower resolution model might have boxes that are hundreds of kilometers wide, but the higher the resolution, the more boxes you have, and the clearer and more detailed the picture becomes. Step 2 is programming that rulebook. And this is where the laws of physics come in. The model is coded with all the math that governs everything, from how the sun's radiation gets absorbed and reflected to how clouds form and disappear, all the way down to the friction of the wind moving over the sea. It's really the fundamental science of how our planet works. In step 3, well, this requires some serious brute force. All those calculations and all those boxes need a ridiculous amount of computing power. This chart here just shows the exponential growth in computer speed over the years. This incredible increase in power is exactly what allows modern models to become so complex and so detailed. So you've got your grid, you've got your rulebook, but what are the actual pieces of the puzzle that the model has to simulate? Well, scientists tend to focus on 5 key players in the Earth's climate system. And these are the big 5: the atmosphere, the oceans, all the planet's ice, which scientists call the cryosphere, the land surface itself, and finally the biosphere, which is all of Earth's living things, from rainforests to plankton in the sea. A really good model has to account for all of them. And what's really crucial here is that the model doesn't just simulate these 5 parts by themselves. It simulates how they interact. You know, that constant exchange of heat and water between the atmosphere and the ocean is a perfect example. It's this coupling of the systems that makes the model a true representation of our dynamic planet. Now, this all sounds pretty impressive, right? But it leads to the most important question of all. With all this complexity, how do we know if the model is actually right? How can we trust what it says? So yeah, let's tackle that one head on. Because if you're going to use a model to look into the future, you first have to prove it can accurately recreate the past. Scientists do something called hindcasting. They basically feed the model historical data from, say, the 20th century, things like solar output, big volcanic eruptions, and past greenhouse gas levels. Then they run the model and see if its simulation of the 20th century climate actually matches the real observed climate data we have from that time. And what's amazing is that even models from back in the 1970s have turned out to be remarkably accurate. If the model's past looks like Earth's real past, we can have a lot more confidence in its future. So once a model is tested and validated, it can finally be used to do what it was designed for, exploring the future. But there's a really key distinction we need to make about what these models actually produce.
And honestly, if you take one thing away from this, let it be this. Climate models do not make predictions like a weather forecast for tomorrow. They create projections. See, a prediction is a single statement of what will happen. A projection, on the other hand, is an exploration of what could happen depending on the circumstances. And those circumstances, they largely depend on us.
So scientists run the models using different scenarios. You can think of them as different storylines for the future, based on the choices we make. For example, what does the future look like in a world with very high emissions versus a world with very low emissions? The model then projects a whole range of possible outcomes for each of those paths, not just one single future. And our ability to map these futures is getting better all the time. As our computers get more and more powerful, the models get more and more detailed. We're moving from these kind of blurry, low-resolution global pictures to much sharper, high-resolution regional ones that can give us a way clearer view of what changes might actually mean for a specific place. So in the end, you see, a climate model isn't some crystal ball telling us our fate. It's much more like a map. It shows us the different roads that lie ahead, all laid out by the laws of physics. It shows us where our choices could lead. And the fundamental question it leaves us with is, which path are we going to choose to take?